Hello, welcome to Semantic Vector Search presentation. My name is Stanislav Stalpolsky. I'm a search and ML architect in Gridnomics, and I will be presenting today with my colleague Eugene. So I'm working with search for last 10 years. We build a lot of big search platforms, Lucene and not Lucene based. And for the last 5 years, I'm working with machine learning and deep learning especially. I love machine learning and information retrieval and robotic. And I have Eugene with me today. Eugene?
Hello, guys. My name is Eugene Steinberg. I'm technical fellow and founding engineer at Gridnomics. These days, I'm heading our digital commerce practice, and I will today co-present with Stas on a very exciting topic, semantic vector search. We are very interested in this topic for the last few years, and very glad to be here with you.
Okay, Eugene, go ahead.
Yeah, let's. So today we are going to talk about search, and we will talk about why in many situations e-commerce search and product discovery queries do not provide results we expect from it, and how to make the search better. So as you know, in majority of the approaches to search, many e-commerce queries are typically trying just to match the parts of a query or terms from a query to the data which we have in the products of e-commerce products. And then very often, this is the main approach to product retrieval and to search in our case. However, in many cases, some very legitimate queries from the customers are not finding a good matches because we do not match data especially well. And that often leads to zero results page or completely irrelevant results. And of course, we all know that if the customers can't find it, they will never buy it. So our goal as a search engineers, as a relevance engineers, to always find relevant product for our customers. Let's go to the next slide. So why we are getting those zero and irrelevant results? There are many reasons, and we can classify those reasons mostly on those few broad categories. Very often we have an out of vocabulary search, which means that we have a term which our customers are using, but that term doesn't exist in our catalog and attributes or product descriptions, or doesn't exist in our synonym base or knowledge base. Very often our customers do not even talk about the attributes of the products which we want to buy. We are talking about their problem. We are talking about the symptoms which we have, like I have a problem, like what kind of product can help me. And in this case, the traditional search is pretty clueless about how to retrieve relevant products which can solve a particular problem. Sometimes customers are inspired by a particular theme, and they are going to talk about Black History Month or some other kind of thematic, Madonna dress. And in this case, again, we not often have this kind of data in our product catalog or knowledge base to satisfy those kind of queries. Compatibility queries, when we are searching for something which complements the different products, or even the non-product searches, sometimes when customers are just searching for something which does not exist in our catalog, and they have to be referred to a different part of the site, is also a problematic kind of searches. So let's look at the next slide and the evolution of the product search which we built over last probably decade or more. So it all started with a typical traditional approach of full text search. When we started to build the systems which are based on the traditional information retrieval techniques, and those techniques were developed for the large articles, full text search kind of scenarios. And the main approach is to find the terms which customer used in the query and match them to the same terms which we can find in the data, and then rank the results by the frequency of those matches. Sometimes we augmented this kind of solution with large lists of synonyms, trying to improve the ability to understand the queries. but it all had a lot of deficiencies with false positive matches, situations when the term is misunderstood in a different context. So the next big advancement was when we migrated to the ideas of a concept search, and that's when we started to match things, not strings, and we started to match the particular kind of combinations of terms in a context of a particular field, and perform things like semantic query parsing. And we expanded our synonym base with a lot of different types of linguistic relationships, things like one-side synonyms, things like instructions to not associate a particular terms together with a different context, and in general knowledge graph about a particular domain, which helps to better understand customer queries. And up to this day, it's one of the most powerful technique in the industry, and it's often augmented with some business rules to improve relevance, and more often it's augmented with a different machine learning approach to re-rank or learn to rank, using the customer behavior data to re-rank some of the top results to drive up the relevant search results based on the way how customers are interacting with the products. And the next great idea which we will be focusing on today is to fully embrace the power of deep learning and natural language processing, and depart from the idea of trying to match a particular terms in a particular data fields inside the products and go completely into the vector space. And the main idea here is to encode both products and queries as a semantic vectors. And the reason why we call these vectors, which are encoding products and queries, as semantic vectors, is because they carry meaning, which means that the products and the similar products will be sitting together in this vector space very close, and they will be close with their corresponding queries. And we will be able to convert the problem of matching the terms to the matching vectors, which is very well solved problem. And to make all the system work, we will need to train our deep learning model and natural language processing model on a lot of domain data and a lot of customer behavior data to drive the correct representation of our products and queries with the vectors. So that's the story which we will be talking about today. So this is a great idea, but how to pragmatically apply it to the e-commerce solution? So if we look at the typical distribution of e-commerce, we will see that we have a combination of head, torso, and long tail queries. And head queries are usually very popular queries, and they're very simple, like it's category, name, title, combinations of those. And those queries are very well served by the typical traditional solution when we just match what customers are asking to the particular attributes of the products. However, if we go towards the long tail, we very quickly see that the queries become much more complicated. They start to involve unknown terms. They start to involve symptoms and out of vocabulary terms. And this is when the vector search or semantic vector search really shines. And then this is when we can prevent zero results, and we can drive the relevant results, even in the situation when we didn't see this particular term in our data, based purely on the deep learning understanding of the query and a lot of information about customer behavior in the context of similar queries which we can accumulate. And Stas will talk about the details of how to make it a reality.
Thank you. So the core idea under the hood of this process is to have a neural network, especially trained model, which we will be able to get user input as a text and convert it into a query vector, which we call embedding. And this special network can input search queries and the product descriptions and place them all together into the big multidimensional space. And the specialty for this network is that the products which will be neighbors to each other will be similar to each other. And the query neighbors of the search query will get the relevant product itself. So if we will place everything in the same dimensional space and we want to find relevant product for the search query, we just need to run the simple algorithm called KNN, K-nearest neighborhood search, and find the product embeddings, which is the closest to this query embedding. And that's how the system will retrieve the document which it thinks relevant for this query. But when we're talking about the special model, let's talk how we can create the special model. So we have lots of models that can convert query to embedding. There's a whole new bunch of family of transformers which take text as the input and produce embeddings. But then out of the box, the node itself is working very good for placing products close to each other. We can improve this process by providing proper training data, as always. And this training data will consist from the three main elements. We will take the search query as an anchor. We will use products which we think relevant for this query as a positive sample. And we will use product which we think is not relevant for this query as a negative sample. And training for this network will be to optimizing vector distance between the query embedding and the positive embedding. So we will bring them closer to each other during the training, and we will push aside query embedding and negative embedding, so they can be far away from each other. Running this algorithm for multiple times, we can reach model generalization. So it will not only work for the queries which we will send to her, but it will try to generalize the whole concept for the query and will work on even for the new query which it never seen before. And when we're talking about this training data, the biggest challenge here will be to finding a negative sample, because we always know which signals we can use to find the positive product, but the negative is something that have a gap, and we not always sure which product is not relevant to the query. It can be new products. They can have no signals because they're new. They can have no signals because it's never been shown to a user. So there are several different complex techniques, starting from the simplest random sampling till the more deep complex of intersecting attributes, which we can use to find these negatives. And this is one of the challenges that we're facing during this training. Also, we can have not only text as input. In most papers that right now people submitting, they exploring the possibility when you have text input from the query and text description of the product. And that's happening because most of the open source data sets have only text description for the product as a single line. But in real world, in the e-commerce catalog, you have much more information you can use to feed this neural network with more rich and more enhanced signals. It's not only starting with product description, it's also including a structured catalog with different separate attributes which can be relevant. It also can include product image information, which is also can be relevant for some categories. As example, if we're talking about fashion category, the product images have much bigger impact on the result than even text, because it's more visual information that something in some cases you don't even can't describe. As example, if I'm looking for a t-shirt with red lines, red lines may be not mentioned inside the text description, but it can present on the image, and that can be a very strong signal for the neural network under the hood. And to combine all these signals together, we have to come up with some complex joint for these features. And in our use case, we're creating a reference model which consists from two big parts. The part which will be used in real time and part which will be used for offline processing. In real time, we will focus only on query embedding. We will take the simple text as an input. We'll provide several layers which will convert this text into word embedding. And then we will use the sort embedding for search. As an offline process, we will take product. We will try to extract all useful information from it using different techniques for encoding, including simple bigram text encoding or transformer encoding, or even using state-of-the-art convolutional neural networks to extract features from the images. After we extract all these features, we will combine them by joining them together and sending it to the pre-final fully connected layer. That will help us to aggregate all this information and will set a proper weight during training for all these features based on this importance. And the final layer of this big neural network will be the same layer which we're using with original real-time query, because if we will place the two different neural networks, the dimensionality distribution for the final embedding vector will be different. But if we're using the same layer, it will be the same coefficients for the query embedding and for the product embedding. And they will be distributed well inside multidimensional space when you're trying to do the actual search. And during the several projects which we've accomplished with semantic vector search, we've found that there are several key aspects that you should follow when you're trying to do this feature join. First of all, don't try to use pre-trained networks. It's happening for transformers and it's happening for image embeddings. It's always good to fine-tune your network before you're doing actual feature extraction. It also will be useful if you will use a visual search neural network for image feature encoding, because it will provide more better feature. Also, the key importance is to use trigrams, because it will allow your vector search to handle misspelling as well. From the things that you shouldn't use, I can also mention that you should not use negative products which just have low CTR metrics. They can confuse your networks, because sometimes product is not being clicked not because it's not relevant. Product being clicked because the price is too much, because the image is bad, and so on. And if we will try to feed neural network with negative samples like this, it will confuse you a lot. So when we have this neural network, let's try to talk how we can use this in real world application. And there are two big scenarios for this. One, we can have this fallback. When we don't have any result, we can use our neural network just as a fallback case and show something which we think is relevant, even though the original search, it doesn't have any result. In this case, if we save, it's easiest and the simplest integration. We just fall back if we don't have result and show result for semantic search. The more complex use case is when we're trying to join results from the regular search and from the semantic vector search. In this case, we can have different heuristic how we can achieve this, and we can compute metrics, compute how we can how we match the query. Did we understand it well? If we did understand it well, we can return regular search. If we did not understand it well, we can return semantic vector search, or we can just have a lookup for the query present in head. If we've seen this query before, we probably think that the regular search will handle it better than vector search. There are many scenarios like this. And it's always challenging to find and compute proper metrics when using joint metrics, but it's still a solvable task, and it will give you much better result than just a fallback. So let's summarize. Semantic vector search is what the industry is going right now. Every big company is trying to play with it, and there's lots of success stories for this. But it's still not a silver bullet. It's not solving everything, and it's always tricky when you have a cold start. You can try use this model from the cold start, but you definitely should invest into this, and you definitely should try it out, because that's the future of the search. And that's our presentation, and I will be glad to answer all your questions. And happy searching.